now we are ready to write down the very important part of this particular chapter or topic, which is called the properties of the region of convergence. Properties of the region of convergence, because our understanding of the ROC is crucial in terms of the application of the Z transform. Okay. So, we will make the following statement. Assume that x of z, the Z transform of the sequence x of n, is of the rational form P of z by Q of z. Rational form P of z by Q of z. Okay, this is x of z. Why do we want that? Because that will then tell us what are the zeros and poles. Zeros of P of z are the zeros of x of z, zeros of Q of z are the poles of x of z. So, therefore, we will get the easy to get the expression. Okay. So, property number 1. The ROC is always a ring, or a disk in the Z plane centered at origin. Okay. When do you get a disk? When you get excluding z equal to 0, you get all the way up to going all the way to infinity. So, basically it looks like a small exclusion and the entire region, that is a disk. A ring is when you get two circles on either side and the region in between. So, the representation is that the ROC is always specified as being greater than a radius RR, less than a radius RL. Okay, we will explain why we are introducing this notation. And this RL can go all the way to infinity, and this RR can go all the way to 0. R goes from 0 to infinity. So, you can have all the way from 0 to infinity, or you can have a ring in between. So, what we say is that a ring or a disk means it is a annulus region between two circles. The two circles, the radius of the outer circle can go to infinity, the radius of the inner circle can go to 0. So, basically what you will get is a ring or the entire Z plane with exclusion of possibly Z equal to 0 and Z equal to infinity. Okay, property number 2. This is a well known, this is a property that it's almost something that we have stated it, but let us write it down. The discrete-time Fourier transform converges uniformly if ROC includes the unit circle. Okay. And since we are going to be referring constantly to the unit circle, the short form notation is mod z equal to 1 or r equal to 1. Okay. More often we will use mod z equal to 1. That means that is the circle with radius r equal to 1. Number 3, again a property that we have already stated, the ROC cannot include any poles. It has to be free of poles. It can be outside of a pole, it could be inside of a pole, but it cannot include that circle which contains a pole. Number 4, most of the sequences that we are going to be working with are finite length sequences. So, if x of n is of finite duration, is a finite duration sequence. Okay. Now, what do we mean by a finite duration sequence? That means it is defined between two integers n1 and n2. It could be 0 and 10, minus 5 and plus 5, it does not matter. It is between two integers. They can be positive or negative, but at least they are finite integers. And to specify that they are finite integers, this is the lower limit is greater than minus infinity, the upper limit is less than plus infinity. So you cannot go to infinity, because if it goes to infinity, then it becomes an infinitely long sequence. So two finite boundaries on both sides. Okay. In this case, then the ROC is the entire Z plane. Entire Z plane except possibly Z equal to 0 and or Z equal to infinity. Okay. Now, what is the simplest way to check what is included and what is not included? Look at the expression for x of z. If it has the following term, this is x of 0 plus x of 1 z power minus 1, this means z equal to 0 is a pole. Okay. And on the other side, if you have x of minus 1 z, then z equal to infinity is a pole. Z is equal to infinity is a pole. Okay. So if you have both positive and negative powers of z in the expression, then both are excluded. If you have only the negative powers, then you will have the 0 excluded, otherwise infinity is excluded. So again, finite length sequences are the safest to work with, because Z transform will always exist. The region of convergence is over the entire Z plane, unit circle is included, DTFT exists, and we also make the statement that the only thing that you have to worry about in a finite length sequence is whether Z equal to 0 is included, Z equal to infinity is included or excluded. We have to check that. Okay, now comes the important observations that we had made, but let us make it more formally. So if x of n is a right-sided sequence, that means it is starting at some integer and then going all the way to infinity. X of n is a right-sided sequence including a causal sequence, right-sided sequence. Okay, this means that the sequence is identically equal to 0 below some integer limit, right. So it is in the region n less than n1. In this region, the sequence is identically 0. That means it is non-zero starting at some point and then going towards infinity. Now this n1 has to be less than infinity, just so that you don't get the you basically actually get a sequence, because if it is n1 is sequence is 0 all the way up to infinity, then it's a 0 sequence, right. So a right-sided sequence starts at some integer and then is non-zero to the right and 0 to the left. Such sequences will always have a region of convergence which is given to be greater than a certain radius. ROC will be of the form mod z greater than RR. Subscript R is for a right-sided sequence. Okay. And this RR is determined by the outermost pole. There are many poles. It is a right-sided sequence, so it has to be greater than some R. So you take the outermost pole. Outermost pole will be the region of convergence of outermost pole of x of z. Okay, and this is the understanding of region of convergence for a right-sided sequence. Now the counterpart will be a left-sided sequence. Left-sided sequence, let us write it down. X of n is a left-sided sequence if the sequence is identically 0 for n left-sided sequence, so n greater than n2. Some integer beyond which it is completely 0, and this has to be greater than minus infinity. Again, the infinity part, don't worry. Left-sided sequence starts at some point and becomes non-zero. Right side, left-sided sequence starts at some point and then is non-zero in the to the left. Okay, in this case, the ROC will be mod Z less than RL, and since we cannot include any of the poles, this means that RL should be the innermost pole of x of z. Pole of x of z. So that will be the region of convergence. Now remember, if it's a right side, I mean if it is a sequence which has got positive powers of which has got for positive n, then you may have to exclude z equal to 0. Possibly the region of possibly exclude z equal to 0. In the same way, you may have to write down for the previous one, right-sided sequence, you may have to possibly exclude z equal to infinity, depending upon whether you have positive or negative powers of z. Possibly exclude z equal to infinity. Okay, but again, the z equal to 0, z equal to infinity is just for completeness and correctness. Most of the time we are interested to say what is the region of convergence in the finite z plane that is where it is valid, and does the unit circle fall in the region of convergence. All right. So the last two properties, and then we will conclude today's session here. So property number 7, a two-sided sequence. Okay, that is a sequence that is neither right-sided nor left-sided. A two-sided sequence. Okay, is an infinite duration sequence that is neither left-sided nor right-sided. Neither left-sided or right-sided. Okay. Now let us see how to analyze this one. X of z equal to summation n equal to minus infinity to infinity x of n z power minus n. Because it's a two-sided sequence, it's got both positive and negative sides of the origin. So I will write it as two parts, n equal to 0 through infinity x of n z power minus n. This is a causal sequence, right-sided sequence. So therefore I will get a region of convergence for this, which will be given by mod z greater than RR. Multiple poles will be present. If they are present, take the outermost pole, that will be the region. Then the second part will be summation n equal to minus infinity to minus 1 x of n z power minus n. This is a left-sided sequence. It is a strictly anti-causal sequence, and this will have a region of convergence which is mod z less than RL. So basically the innermost pole. Okay, and such a sequence then has got the intersection of these two regions of convergence, which says mod z greater than RR less than RL, and this could go, RR could go all the way, it could start from origin R equal to 0, and it could go all the way to infinity. So basically a two-sided sequence is what has got these two boundaries. You take the to the right of the outermost pole and to the left of the innermost pole, and you must find a region of convergence. Remember that the poles are different because one is a right-sided sequence, the other one is a left-sided sequence, and they are two different sequences. So you take the outermost pole of the causal sequence, the innermost pole of the non-causal sequence, and then you will get the this region. Okay, the last one, which is looks like an obvious statement but still should be stated, the ROC must be a fully connected region, must be a fully connected region. Okay. So, there is no region of exclusion, right? Either it is to the right of a circle, to the left of a circle, or between two circles. There are no regions where it is not, that region of convergence is not valid. So, in other words, this is another way of saying no poles, right? In the region of convergence, every point within the region of convergence must satisfy the convergence of the Z transform. So, basically another way of saying that there are no poles in the region of, no poles or discontinuities in the region of convergence in ROC. All right. So, this gives us a complete introduction to the Z transform. We saw what the Z transform is. We saw that it's a generalization of the discrete time Fourier transform. We said that always we must specify a region of convergence to get a unique representation of the time domain sequence. And if the region of convergence includes the unit circle, then the discrete time Fourier transform will exist. We have written down 8 properties of the region of convergence. We have looked at some examples of the computation of the Z transform. So, what I would encourage you to do is to go through the examples that we have looked at, look at the examples that are there in the book. Particularly, we have looked at topics which are there in the sections 1 and 2. Please go through those examples, and we will then pick up from section number 4 in the next session. Thank you.